Hello, in the last video I have spoke extensively about Chebyshev's inequality. Today I am just going to briefly introduce the Chebyshev's inequality and then move on to one of the most important results in probability theory and analysis, namely the dominated convergence theorem, which is probably going to be your lifelong friends as long as you do probability theory and any type of analysis, especially those related to limiting, where you are trying to find limits of integrals or limits of expectations. Anyway, so Chebyshev's inequality, as I mentioned, that it is mainly related to finding the probability of deviations from mean exceeding some given value. So X represents a random quantity. It may be the price of a share or stock or price of gold, or it may be the magnitude of earthquake. So generally we have some idea about averages from historical data. So we want to know how much in a given situation can the average can a random quantity deviate from its average. Deviations can be both above and below. So that's why we're looking at the absolute value of the deviation. So the probability of deviations from mean is hard to compute in general, but fortunately Chebyshev's inequality gives you a very nice upper bound provided the variance is finite. And here the interesting part is that you don't need to know the exact probability distribution of X. And in fact, we can, as I said earlier, that if you have historical data, then we know how to estimate the mean and the variance even without knowing the details of the probability distribution. That we will talk about maybe later once we are done with the asymptotics part. So now I come to the next result, dominated convergence theorem. It is about, so I have a sequence of random variable xn converging to another random variable x pointwise on the probability space. Under what conditions expectations of xn's will go to expectation of x. In general, it is not true. We need some condition. So that condition is the one from where this theorem gets its name. It is a dominating condition. That means we find if all the random variables, all the xn's are uniformly bounded by one random variable, which is L1, then this convergence would hold. Now in this note I have written mode of x. Then now there is nothing wrong with it, because x is L1 means expectation of mode of x is also finite, but we can state it slightly generally, so I have stated it separately. So I am asking the same question. I have a sequence of integrable random variables converging pointwise to a constant or a random variable on the same space. Does the corresponding sequence of expectations also converge to the expectation of the limit? Means if the limit is a constant, then expectations will converge to the same constant, and if the limit is a random variable, then expectation should go to the expectation of that random variable, not other random variable. So the dominating condition here is that all the xn's must be dominated by a one common random variable y. Now this y may not be equal to a mode of x. If it is equal to mode of x, then nothing like it. Then if y is also having finite mean, so then expectation of xn's will converge to expectation of x. So the main thing is that we should be able to bound it above and below by one common random variable having finite mean. Why I am saying bounding above and below? So a mode of xn less than x means xn is between y and minus y. So really the point is that we are bounding all the xn's by one common random variable having finite mean. So that is the main point to remember. Now I will show that why this condition is important. So without this dominating convergence, you may not have xn's going to the same xn's. You may have a situations where xn's converge to some constant, but expectation of xn's not necessarily converging to the same constant. So here I have given an example. So here x is a random variable, and I am assuming that it is following uniform distribution. In one of my previous notes, I have given you a list of common continuous distributions like a uniform, exponential, normal, and student's t distribution. So you know what is uniform distributions, but still I have a recap over here. X follows uniform distribution means X is a continuous random variable which is taking the values between 0 and 1 with probability 1, and that is, it is non-negative proper fraction valued. And secondly, probability x less than equal to y is y, where y is any proper fraction. Okay, of course, if y is more than 1, then it will be 1. If y is negative, then it will be 0. So that's obvious from here. So the important part is, as long as y is a proper fraction, this probability is exactly equal to y. That is where from it gets its name, uniform distribution. It is like Lebesgue measure on 0, 1. It is like Lebesgue measure on Borel subsets of 0, 1. So now you see, now I am defining x and w as how that also for each w in the sample space, x and xw is a non-negative number. So I compare it with 1 by n. Either it will be more than 1 by n or it will be less than 1 by n. If it is less than 1 by n, then I call x and w to be corresponding image under x and w to be n, and otherwise xn takes the value 0. So each xn is a two-valued random, simple random variable. So what will be expectation of xn? It will be n into corresponding probability. The corresponding probability is probability x less than 1 by n. Now, so instead, so by this formula, this probability will be 1 by n. So n into 1 by n, it is 1. So you see, expectations or xn's are all 1. But what happens to x and w? Now let me take a w for which xw, so x for w in s, xw's are non-negative proper fraction. Now let me take a w for which xw is a positive proper fraction. Now if xw is a positive proper fraction, then you know that since 1 by n's are going to 0, you can find a nw such that for all n exceeding nw, 1 by n is less than xw, right? This has to happen if 1 by n has to go to 0. So this means what? What is the limit of and what is the corresponding x and w? So when xw is less than 1 by n, when xw is greater than 1 by n, as is the situation here, then x and w's are equal to 0. So x and w's are 0 for all such n exceeding nw. So x and w's are going to 0. So these x and w's are going to 0 for all w that is for which xw is between 0 to 1. Okay. And for uniform distribution, it is a continuous distribution. So whether you take closed interval or open interval, this probability is going to be 1. So with probability 1, for all w's, x and w's are going to 0. But you see, expectations of xn's are not going to 0. They are going to 1. So this is what the DCT fails. So I would have wanted expectation of xn's also to go to 0, but that did not happen. Why did not happen? Because the DCT dominating condition is not there. That is, since each x and w takes n with positive probability, the probability being probability of x less than 1 by n, which is 1 by n. So for each n, there is a small probability 1 by n that x and w can take the value n. So you cannot find one random variable y which will dominate all the random variables xn. Why not? Because yw is suppose y is a non-negative valued random variable. So for every w, yw is a non-negative number. So by Archimedean property of real number, you will find an n such that n is greater than yw. So corresponding xn will not be dominated by y, because there will be a positive probability that the xn will be greater than y. So we cannot find any common dominating random variable in this case. So therefore the DCT does not hold in this case. So remark, another important point here is that what kind of convergence are we having here, x and w's. You see, if xw happens to be 0, if xw is 0, then this condition is holding for all n. So for every w for which xw is 0, x and w will be equal to n, right? So for such w, x and w will be a divergent sequence. So you see, in this case, the convergence that I am saying is holding only outside this set. Which set? The w's for which xw is equal to 0. But fortunately, since x is a continuous random, so probability x equal to 0 or probability of a is 0. So we are having convergence, but for w's outside a set A which has probability 0. So it is similar to pointwise convergence but not exactly. So this type of convergence is called almost everywhere or almost shear convergence. And now I am generalizing the definition. Suppose I have a sequence of random variable and another random variable on the same space. X and w's are converging to xw's, but not for all w, but for w's outside a set which has probability 0. So then we call it just like in this example. In this example specifically the set is and those w's for which xw is 0. So in general we are saying if you can find an event A such that P of A is 0 and x and w's converge to xw outside that A, then that that is we call almost shear convergence or almost everywhere or strong convergence. Now can you see it similarly? Can you compare it with almost pointwise convergence? Sure. If A happens to be equal to phi, I said that A can be any event. If you take A equal to phi, then probability of phi is 0. That is the first property we proved, right? And a phi complement is S. So for every W in S, if x and w goes to xw, that is what is the pointwise convergence. So we can think of the pointwise convergence as almost shear convergence when as a special case when this A is phi. So pointwise convergence is a much more stricter condition when this A is specifically equal to phi and A complement is S. But the almost shear convergence is a slightly weaker concept because A need not always be equal to phi. So you know this, right? P of A equal to 0 does not imply A is empty. So here is an example. Here P of A is 0, but it is not an empty set. So if A happens to be any other set which is not phi but probability of A is 0, and as I said there would be events like this, especially when S is uncountable, then this can happen. Here you see that in this set convergence is not happening. In fact, in this set xn's are a divergent sequence, so we cannot say that x and w goes to 0 for all w in omega. So this is not pointwise convergence because in this event the convergence is not happening, but it is happening outside this event A, but this event has probability 0. So I hope now it is clear that almost shear convergence is very similar to your pointwise convergence, but it is slightly weaker in the sense that here A could be any set with probability 0 and you are having convergence outside that set A. Okay, thank you.